If you were dropped onto the coast of Iceland in the year 874 AD, you would notice something terrifyingly absent. There are no trees, there are no caves, there is no shelter. You are standing on a volcanic rock in the middle of the North Atlantic, and the wind is not just blowing, it is screaming. It tears the heat from your body 25 times faster than still air. In these latitudes, hypothermia doesn't take hours, it takes minutes. The Vikings who landed here were the fiercest warriors in history, men and women who laughed at swords and navigated oceans. But standing on that black sand, looking at a horizon devoid of timber, they faced an enemy that no axe could kill. They faced the absolute zero of a Nordic winter without a single log to build a cabin. This presents a paradox that seems impossible to solve. How do you survive a winter that freezes the ocean itself, when you have no wood to build walls and no coal to burn for heat? The answer lay right beneath their boots. It wasn't in the stone and it wasn't in the drift ice, it was in the grass. But not in the way you might think. They didn't weave it, they didn't eat it, they engineered it. They realized that to survive the atmosphere, they had to bury themselves in the earth. But this wasn't just digging a hole, this was architectural alchemy. They had to turn dirt into a fortress that could breathe, move, and hold heat better than modern concrete. If they failed to understand the physics of the soil, the roof would collapse and crush them in their sleep. If they succeeded, they would unlock a secret of thermodynamics that we are only just rediscovering today. But first, they had to survive the first night. To understand the genius of the turf house, you must first respect the enemy. In Scandinavia and the North Atlantic settlements, the enemy is the wind. We call it the North Atlantic Oscillation today, a weather phenomenon that drives freezing air from the Arctic directly into the path of human settlement. We are talking about sustained winds of 60 miles per hour, with gusts reaching hurricane force. A standard wooden wall, like the ones used in mainland Europe or southern England, has gaps. Under that kind of pressure, the wind acts like a liquid. It forces its way through the tiniest crack, finding the warm air inside and sucking it out through a process we call infiltration. A modern tent would be shredded in seconds. A stone castle, cold and conductive, would act as a refrigerator, sucking the body heat out of anyone sleeping against the walls. The Vikings arrived with a memory of the great timber halls of Norway, vast, high-ceilinged structures made of massive pine logs. But in Iceland and the barren reaches of Greenland, driftwood was a currency more valuable than silver. You could not waste it on walls. You saved it for the frame of the roof and for ships. This scarcity forced a desperate innovation. They were trapped between the freezing ocean and the volcanic interior. They needed a material that was abundant, easy to harvest, and possessed an insulation value high enough to trap the meager heat of a small fire and human bodies. They looked at the landscape, a landscape of bog, marsh, and grassland. To the untrained eye, it was just wet ground. To the desperate engineer, it was a matrix of millions of tiny air pockets held together by the strongest fibers in nature, the root system. Imagine the first attempt. The sound of the spade hitting the wet earth is a dull thud, barely audible over the roaring surf. The first settlers likely tried to pile the earth up, much like a burial mound or a simple dike. But earth is heavy. A cubic meter of wet sod weighs nearly 2 tons. When you pile it up without structure, it slumps, it slides, it turns back into mud when the rains come. And the rains always come. Early accounts and archaeological layers suggest a period of trial and error that was likely fatal for many. You can hear the sound of the wind howling outside, a constant shrieking reminder of the thin line between life and death. Inside these early crude structures, the dampness would have been suffocating. If the walls are just piled dirt, they hold moisture. The water freezes. The frost heave pushes the walls apart. You wake up in the pitch black of winter, and the wall next to you has buckled. The roof beam is groaning, stressed by the weight of the snow and the shifting, heavy walls. The cold isn't just outside, it is radiating from the damp earth itself. They were trying to build walls, but they were thinking like carpenters, not like masons of the earth. But just when it seemed the colony would fail, they discovered a hidden property in the soil that would change everything. The turning point came with the realization that not all grass is created equal. The Vikings, being farmers at heart, understood the root systems. They discovered that in the marshlands, the root systems of the sedge and grass grew so thick and tangled that they formed a natural composite material. It wasn't just soil, it was reinforced earth. The roots acted like the rebar in modern concrete, providing tensile strength, while the soil provided the compressive strength and thermal mass. The engineering insight, the aha moment, was the realization that this material contained trapped air. Stationary air is the best insulator in the world. By harvesting the top layer of the bog, where the roots were densest, they weren't just harvesting building blocks, they were harvesting millions of microscopic pockets of insulation. They developed specialized tools, scythes and spades, designed not for farming but for precision cutting. They learned to cut the turf into specific geometric shapes. This wasn't random digging. This was the standardization of a biological brick. They realized that by manipulating the angle of the cut, they could make the blocks interlock. Gravity, which had been their enemy causing the walls to slump, would become their ally, locking the walls tighter together the heavier they got. This was the birth of the clambra, the herringbone pattern that would define Norse architecture for 1,000 years. It was a shift from piling dirt to weaving a wall. Let's walk through the construction. It begins in the late summer, when the ground is thawed but the grass is at its strongest. You don't just dig, you peel. The men would cut strips of turf, sometimes a meter long, called strengur. These weren't just clods of dirt, they were carefully measured strips. You can feel the weight of them in your hands, heavy, damp, living matter. The smell is rich and metallic, the scent of peat and ancient organic decay. They would lay a foundation of stone first. This was crucial. You cannot lay turf directly on the soil, or the moisture will wick up through capillary action and rot the walls from the bottom up. The stones acted as a damp course, a barrier between the wet earth and the living wall. On top of this stone ring, they began to lay the turf. But they didn't stack it flat like bricks. They laid it in a herringbone pattern, one strip leaning left, the next leaning right. This is the clambra method. Why? Because as the turf dries, it shrinks. If you stack them flat, gaps open up and the wind gets in. But in a herringbone pattern, as the turf shrinks, the blocks settle deeper into each other. The wall becomes tighter, denser, and more impermeable over time. The tactile sensation of building this way is intimate. You are pressing the roots of one block into the grass of another, knitting them together. You are building a living organism. But nature is relentless. Just as the walls are rising, the autumn storms hit. This is the crisis point in the construction and in the survival of the settlement. The sheer weight of a turf house is immense. A roof covered in sod becomes a sponge when it rains. The timber frame inside, that precious, scarce driftwood, begins to creak under the load. If the angle of the roof is too shallow, the water pools, the turf turns to liquid mud and the roof collapses, burying the family alive. If the roof is too steep, the turf slides off, leaving the structure naked to the freezing wind. There is a frantic urgency in the air. The days are getting shorter, the light is fading. The wind is picking up, tearing at the exposed edges of the work in progress. You can imagine the scene. Men and women working with bleeding hands, trying to finish the gable ends before the snow starts. They run out of the prime root-heavy turf and have to use inferior soil. The walls start to bow outward. They have to shore them up with timber they can't spare. It is a race against thermodynamics. If they cannot seal the structure before the temperature drops below freezing, the wet mortar of the earth will freeze, expand, and shatter the integrity of the wall before it has even set. But here is the craziest thing. The stronger the wind blew, the stronger the house became. While a wooden wall might shatter under the pressure, the turf house actually used the wind to its advantage. To understand this, we have to look at how they engineered the aerodynamics. They stopped trying to build tall, imposing halls like they did in Norway. They lowered the profile. They built the walls thick, sometimes 2 or 3 meters thick at the base. From the outside, the house didn't look like a building. It looked like a hill. This was intentional. When the hurricane-force winds hit a vertical wall, they create a pressure spike that can tear the wall down. But when the wind hits a turf house, it flows over it. The house uses the Bernoulli principle. The wind speeds up over the curve of the roof, actually creating a slight lift that pulls the roof up. This lift counteracted the heavy weight of the sod, preventing the heavy roof from crushing the timbers during a storm. The harder the wind blew, the lighter the roof became on the frame, yet the house remained anchored to the earth. They also refined the roof design to solve the water crisis. Between the wooden roof boards and the heavy turf, they laid a layer of birch bark or fine twigs. This was the drainage layer. It allowed the water to run off the roof underneath the grass, but above the wood. It kept the timber dry while keeping the insulation wet enough to stay alive and knit together. Then comes the test. It is mid-January. The sun does not rise. The world outside is a void of white noise and lethal cold. The temperature drops to -30 degrees Celsius. The wind chill pushes it to -50. If you were to step outside, your eyes would freeze shut. The storm creates a whiteout so complete that you could get lost and die 5 meters from your own front door. But inside, the sensory experience is shockingly different. You step through the low, dark entrance tunnel, a design feature that acts as a cold sink, trapping the heavy cold air before it reaches the main room. You enter the main hall, the skali. The roar of the wind is muffled to a dull throb, distant and irrelevant. The air is still. It smells of wood smoke, dried fish and unwashed wool, but it is warm. The temperature is a steady 10 or 15 degrees Celsius. Not hot by modern standards, but the difference between life and death. The massive walls, meters thick, have absorbed the heat of the fire during the day and are now slowly radiating it back into the room. The family sits on the raised wooden platforms along the walls, the set. Their body heat, roughly 100 watts of energy per person, adds to the warmth. The house is utilizing human thermal energy as part of its heating system. Outside is chaos. Inside is a womb of earth and wood. The result of this engineering was survival. Archaeological excavations of these sites show that while the Vikings suffered from many hardships, they did not freeze to death in their homes. The thermal mass of the turf walls created a thermal lag. It took days for the outside cold to penetrate the walls. By the time the cold reached the center of the wall, the weather outside might have warmed up. The walls flattened the temperature curve, keeping the interior stable regardless of the blizzard raging outside. This stability allowed for something more than just survival. It allowed for culture. In the Badstofa, the main living room developed in later designs, people worked wool, carved wood, and told stories. The insulation was so effective that in later centuries, with fuel becoming even scarcer, the heat from the livestock kept in the basement, combined with human body heat, was often enough to keep the house warm with barely any fire at all. The turf house didn't just keep them warm, it kept their history alive. It was a symbiotic relationship. The humans maintained the turf, repairing the eroding grass, and the turf protected the humans. The turf house is more than just a primitive hut. It is a masterclass in adaptation. It reminds us that for most of human history, we did not fight the environment, we merged with it. We didn't import materials from thousands of miles away. We looked at the ground beneath our feet and asked, what can this do? The Vikings, often remembered as destroyers, were also supreme creators. They built homes that breathed, homes that grew, homes that returned to the earth when they were abandoned. Today, as we look at our glass towers that require massive amounts of energy to heat and cool, struggling against the climate, there is a lesson in the Viking longhouse. It teaches us that true resilience isn't about being stronger than the storm. It's about being smart enough to let the storm pass over you. If you want to discover more forgotten ancient technologies that helped humanity survive, subscribe now and comment below. What type of ancient shelter should we uncover next?